What's up, everyone? Hope you guys have had a good Wednesday. We got participants loading up. I got my screen going. My audio is on. My phone is silent-ish. And got a PowerPoint. Got some questions, some poll questions. Um, I'm gonna have some quizzes that I add, but they're late. So I'm not going to say, haha, rules are for thee, not for me. Instead, what I'm going to do is I'm going to put the quizzes up so that you have some questions related to this content. But I'm going to give freebie questions, or sorry, freebie points for those quizzes. So you'll see quizzes, I think it's B, I can't remember the numbers off the top of my head. But you'll see those up there. You can do them, knock them out, get the sort of practice questions. Um, and there will really kind of be no consequence to your performance on those because I'm going to be making those same numbered quizzes, and everyone's getting credit for those. Same too goes for activities for this week. I apologize for that. Um, and so, yeah, I'm sorry about that. But I'm also not sorry about compensating you with the guys with the points. Because I don't know, it seems like a reasonable approach. So you get the questions, you can answer them, you can look at them and see the sorts of things related to this content. Will there be a practice test? Yes, there will be a practice test. And I think our exam is 2 weeks from today. So I am going to have the practice test for exam number 2 up, hopefully within the next few days. In the event that I said, hey, yeah, I'll have it up by the end of spring break, I apologize for that. I have missed that deadline. But I will have it up sooner rather than later. So right now we have only talked about things that I dropped the ball on. So I apologize. That's like two significant apologies. What I think are significant. Now, with that in mind, we're kind of putting a little bit of a bow on sugars. Um, and the reason I say that is because what we're going to be doing today is talking about the regulation of glycolysis, and therefore the regulation of our well, our central sugar metabolism. Um, Now, in the event that you have already looked at this PowerPoint presentation or this PDF of that PowerPoint presentation, there's like a figure on, I think it's like the third slide or so, that's a little bit intimidating, just because it's like this arrow goes here, that arrow goes there. It's kind of like you're simultaneously trying to read like an interstate highway system and a subway system, but in a condensed area. So we're going to kind of process that and break through, work through that so we can see some good content related to that. Now, with that said, I have a little bit of a question. Would you be able to upload Edpuzzle so I can? Yes, I will. I apologize. I will. I got a question of will I link the Edpuzzle videos? Yes, I will. If you are interested, they are on my YouTube page, which I learned today. I have 1.22 thousand followers. I've always thought that you reserve a decimal place whenever you're talking about millions, but I'm 1,000 air when it comes to YouTube channel subscribers. So I'm at least at 1,220. Could be as high as 1,229. But yes, I will link those. And my YouTube channel is Gray Matter, which I'm pretty pumped about that name. Okay, so I've got a poll question for you guys to take a look at. A glycerol can be metabolized to glucose. True or false? And the answer to this one is true. Um, if you are, if you're thinking about, well, where is this coming from? Um, the first thing that I want to mention is that anything going to glucose, X, whatever, going to glucose, chances are that's a reference to gluconeogenesis. And it's a nice thing to think about glycolysis simply as, and I'm going to go ahead and end the poll here. Um, we had a total of 42 responses, and 38 selected true. So 38 y'all, good job. The other four of you, I'm guessing it was probably just you clicked the wrong thing. So when you think about glycolysis and gluconeogenesis, it's really nice to think about glycolysis and gluconeogenesis as just like totally reciprocal pathways. Glycolysis, going to give you a nice arrow. That's glycolysis. And then it's nice to think about gluconeogenesis as, I'm going to label it as Y instead. Y goes up to here. But, we learned last time that there's a couple of things that are different. First and foremost, the biggest thing when it comes to gluconeogenesis versus glycolysis is this step right here. We're going Drake style and we're starting at the bottom, but we're going to end up here at glucose. But what we need to do is we need to go from pyruvate to phosphoenol pyruvate. And if you remember, there's a little bit of a roundabout course of action to doing that. We had to go take pyruvate, put it into the mitochondria, convert it to oxaloacetate, convert it to malate. Malate gets converted to oxaloacetate, and oxaloacetate then gets converted to phosphoenol pyruvate. Okay, so we have a couple of steps basically to undo the action of pyruvate kinase. Now, up from pyruvate kinase all the way to fructose 1,6-bisphosphate, well, everything between there is reversible. Then we've got to undo the action of phosphofructokinase, and that's done by FBP fructose 1,6-bisphosphatase, ASE, because that's a enzyme that hydrolyzes phosphate off. And one thing that I'd really like to highlight here is that this fructose 1,6-bisphosphatase, it's very tempting to say, oh, well, we're doing the opposite, so we're making ATP. We are not. We're releasing inorganic phosphate. So when we hydrolyze this this phosphate right here, the one that I've just circled, when we remove that phosphate right there, that's just going to release as PI, or inorganic phosphate. So that's going to give us our fructose 6-phosphate that get rearranged, and then that gets rearranged. We go Limp Bizkit on that with the song Rearranged. So we rearrange that to give us glucose 6-phosphate. Then we are again going to use another phosphatase to release inorganic phosphate, or PI. So that will get us back to glucose. Now that's our big overview of gluconeogenesis. Now, if you remember, there are a couple of things that we talked about with respect to, well, other metabolites. For instance, we had lactate. Lactate gets converted to pyruvate. Done. There's also alanine that gets converted to pyruvate through a process known as the Cori cycle, CORI. Now, if I remember correctly, I've heard a handful of people who have gone on to be physicians when they take the MCAT, they're like, oh yeah, I know biochemistry, the Cori cycle. And they have this kind of like shocked look on their face. And I've always felt like it's, to which I think to myself, I mean, a little bit. And maybe that's something that physicians go really in depth on, or I don't know. To me, the Cori cycle is kind of like it's like I don't know. I was about to make some sort of cultural reference, but then I realized all my cultural references are 30 plus years old. At any rate, the Cori cycle. That's how we can convert alanine to pyruvate. And once we get to pyruvate, that goes back up to glucose. Now, the one that's a little bit of an outlier that I wanted to mention that I did on that last question was none other than glycerol. Glycerol can be used to convert or to generate dihydroxyacetone phosphate. I think it's really important to remember this because you need glucose. If you consume a very high fat diet, a high triacylglycerol diet, are you going to have glucose in your bloodstream? You are, because triacylglycerols will be broken down into glycerol and a fatty acid, or and fatty acids. That glycerol can then be metabolized into ultimately make glucose. So if you consume a very high fat content diet, is your blood sugar going to be lower than people who do not? Not necessarily, because you both have a liver that acts to regulate that. So those were the big things with respect to gluconeogenesis and kind of using different metabolites to make, well, none other than glucose. Okay. So I hope that that made some sense, and I hope that that question, if you I guess if you have any questions about that, feel free to go ahead and add them to the chat. Now, what we're about to see, and just buckle up on this one, um, you're going to see a pathway that's like, it can be a little jarring. And boom, there it is. As my relatives from Western Wisconsin would say, oofda. There's a lot to process here. And so rather than just saying, hey guys, we've been in class for 11 minutes, know this, peace, I think I'll go ahead and we can talk about it. So the first thing that I think is worthwhile is to take this pathway or take this pathway and remove lots of the fluff, remove lots of the mess. So, for example, this has what we've learned so far with a couple of additional details. Now, what I want to draw your attention to is some of the things that have been highlighted. These yellow arrows, here, here, here. Those yellow arrows are our irreversible steps of glycolysis. If you look at that, what you'll see is we've got glucokinase slash hexokinase, phosphofructokinase 1, pyruvate kinase. Now, I'd like you guys to respond in the chat, and I'm going to go with more, M for more, or N for none. Um, when we are going from fructose 1,6 bisphosphate to phosphoenol pyruvate, add an M to the chat if there are more than one step, or add an N to the chat if there are no more than that one step. You got some M's in there. You're absolutely right. I'm happy that you see that because that really emphasizes that glycolysis is not merely, let's see, one, two, three, four, five. Glycolysis is not a five-step metabolic pathway. Now, what we've emphasized here are the big points and some points that are important for regulation. Now, the yellow arrows indicate our irreversible steps. PFK1, why does PFK1 stand out? Or why do I always stress that PFK1, yeah, it's irreversible, but it's different? Add to the chat if you know why, or, well, what it is that makes it different. First committed step. Perfect. It's the first committed step of glycolysis. Now, one thing that I want to bring to your attention is that glucose 6-phosphate, that is an intermediate that is used for the production of glycogen, which I like to bring this up because this reversible arrow right here, I want you to recognize that that is why the glucokinase or hexokinase step is not our first committed step because the product of this the product of this first step, that being glucose 6 phosphate, well, where can it go? It could go to glycogen or it could go to fructose 6 phosphate. So glucose 6 phosphate is not committed. So the first committed step is not the glucokinase hexokinase step. All right. Now, when it comes to the regulation of that first step, glucokinase hexokinase step, there's a couple of variables that are worth recognizing. One thing is that glucokinase is in the liver. And basically everything else has hexokinase. So hexokinase is in other tissue. Now, regulators of glucokinase, or one regulator of glucokinase, is fructose 6 phosphate. Okay, now this is a downstream product. Does anyone know a good term or phrase for when a downstream product regulates something upstream or regulates a process upstream? A negative feedback loop. Exactly. So fructose 6 phosphate is a negative regulator. So fructose 6 phosphate, F6P, regulates, and I want to stress this right here, this is in the liver, so this regulates GK, glucokinase. Now, I bring that up because, well, G6P regulates hexokinase. Okay, so if you kind of look at those two staples and remember those, that's going to be very helpful. Now, glucose 6 phosphate and fructose 6 phosphate are both negative regulators, and they are both, therefore, inhibitors of glucokinase or hexokinase. Fructose 6 phosphate does it a little bit more deliberately. It's more downstream, an additional step. This is produced after that isomerization of glucose 6 phosphate to fructose 6 phosphate. Whereas in every tissue but the liver, well, glucose 6 phosphate, the immediate product, is going to regulate the enzyme that makes it. Now, fructose 1 phosphate. So I will try to say the full name, but I will try to write out the acronym for the different molecules. Fructose 1 phosphate, notice how that's written in blue. Fructose 1 phosphate regulates the regulation of fructose 6 phosphate. So F1P, effectively what that's doing is it is blocking the activity of F6P. So F1P stops F6P, I'll say F6P's ability to stop. Didn't happen. So fructose 1 phosphate stops F6P's. F1P stops F6P's ability to stop GK, or glucokinase. Now, can I get a Y in the chat, or if that makes sense, or an N in the chat if you'd like me to revisit that? Okay. Okay, cool. Now, we have kind of a visual of what that looks like. So, actually, yeah. Okay, so essentially, F1P stops F6P. That is unique to being in the liver, or that is unique because this is what takes place in the liver. So our first step, our production of glucose 6 phosphate, done by either hexokinase or glucokinase is going to be regulated in part because it is a um, irreversible step. In addition to that, the products that it makes, whether it's immediately downstream or an additional step downstream, those are going to kind of put the brakes on it. Now, with that in mind, let's think about the different kind of functions. So, when it comes to glucose 6 phosphate, we have a couple of different fates for glucose 6 phosphate. One fate is that it could go to glycogen. Alternatively, it could go on through glycolysis. Now, glucose 6 phosphate, if it goes into glycogen, then that's basically a way that that molecule can be kind of siphoned off. And the liver is absolutely essential for regulating blood sugar throughout the body. So it's helpful as for monitoring that. Now, our next enzyme that we want to get into. So I think that it's helpful to kind of think about these different regulatory steps as the big three and then work out from there. So our first step, our regulators are glucose 6 phosphate or fructose 6 phosphate, F6P or G6P. Those are both going to inhibit our first step, but they're going to differentially inhibit. Fructose 6 phosphate, if you put that into a muscle cell, that's not going to slow down to a significant amount. It's not going to slow down hexokinase, whereas it will in the liver slow down glucokinase. Now, our next enzyme, PFK1. Okay, let's think about what PFK1 does. Well, PFK1 is responsible for taking our rearranged F6P and phosphorylating it. So taking a phosphate from ATP and adding it on to fructose 6 phosphate to make fructose 1,6 bisphosphate. So can I get a yeah or a Y in the chat if you would agree with the statement that ATP is a substrate for PFK1? Yeah. So PFK1 has essentially two major substrates. It's got fructose 6 phosphate and ATP. Now, interestingly, PFK1 is actually inhibited by ATP. So its natural substrate is going to slow it down. Okay, so let's think about this. What are the things that we know about PFK1? And I've harped on this a bit, and I'm fine doing that. This is our first committed step. It's our first committed step. So, if you were to, let's say, you're walking through you're walking around on campus and you see someone and you don't know that person, but you're like, I have to tell you about glycolysis. Go ahead and add to the chat. What do you think you're going to tell them about glycolysis? And I'll give you a little bit of direction. What's the purpose of glycolysis? I can kind of think of like two big responses or two major responses. But if you were going to tell like a stranger, hey, great news, glycolysis exists, and here's why we do it, what do you think you'd say? Break down glucose to pyruvate? Fantastic. I think I would probably add in there, it's a process where we get a bunch of ATP. Awesome. So we're generating ATP. Great. Thank you very much for those responses. Those are great. Now, so if we were to kind of pigeonhole glycolysis as a process or a pathway that is used to make ATP, would you agree with this statement or the idea that ATP is an ultimate product of glycolysis? Like grand view, grand overview. So, yes, it is a substrate. So ATP is substrate. But also, glycolysis is a pathway to make ATP. So, um, critical, I'll say this, these are statements or these are thoughts about PFK1. Critical for glycolysis and process to make ATP. So, although ATP is a substrate, and therefore PFK1 needs to use it, ATP is also a major product of the overall pathway. And you could kind of think about it as if there's a high concentration of ATP present, and I'm just saying an arbitrarily high concentration, that means that glycolysis has been working. It's been going on. It's been, doing its job. So does PFK1 need to be active anymore? Not really, because we've kind of resolved it. Like um, we don't need to make as much ATP because we've got a lot of it already. Now, with that in mind, what we see here on the right-hand side is we see a Michaelis-Menten plot that shows a couple of different things. One thing that it shows is the activity of PFK1. Our y-axis shows our PFK1 activity, so you can think about this as initial velocity, and then our x-axis as substrate concentration. What this shows is this dark blue line indicates whenever there's a low ATP concentration, what happens to PFK1's activity? It's there. It's kind of at its optimal level. Now, whenever we add ATP, I want to draw your attention to this green line right here. What do you notice about the enzyme? Well, when you add ATP, a higher concentration, or sorry, when you increase the ATP concentration, well, what happens to, let's think about that Km. Here's our Km. So in this case, so with no inhibitor, we reach Vmax divided by 2, or we reach half of our Vmax with what concentration of F6P? Well, that would be approximately, I'm going to call that 0.15 millimolar. Could anyone add to the chat that yes, they follow what I'm marking up on this plot here? Add a Y if you follow that. I know that it takes a second to, okay, cool. So this is, we have a Km, I'm going to add a Km of approximately 0.15 millimolar. Now when we add ATP, yes, another substrate, but we've increased the concentration of it. What happens to our Km? Okay, well, out here, what has happened to our Km in the presence of, whatever higher concentration of ATP, our Km has increased to approximately, I'm going to call it 0.95 millimolar. So our enzyme's ability to do the job has diminished. Now, when we add that same concentration of ATP, but we also add AMP at a relatively low concentration, well, our Km ends up kind of here in the middle. And I'm going to call that Km of 0.61. Why 0.61? I don't know. I just kind of arbitrarily decided that. So what that shows is that we can mitigate or reduce the inhibition by ATP with AMP. Now, a great question for that would be why? Well, when ATP binds to phosphofructokinase, there's probably multiple sites in which ATP can bind to it. In one case, it's going to be a natural binding site, and then another place might be a regulatory domain or regulatory site. We'll get into that a little bit more when we talk about hemoglobin and protein function. But that's a little bit of the story why ATP, to a certain point, a low concentration of ATP, PFK1's happy. You go above that, PFK1 says, nah, I'm less interested in working now. Okay, so I'm going to come back to this item down here, inhibited by citrate. But what I want you to take away from this is that PFK1 is inhibited by its natural substrate of ATP. I'll introduce the term here, but we're going to revisit it. This is known as an allosteric regulator. I don't want you to lose sleep about that term right now, but I want to plant that seed so later on we can revisit that plant and see that, yes, it has bloomed. Okay, so ATP is an allosteric regulator. Now, what we are interested in is this right here. Okay, that's our PFK1 step. What we just talked about was this right here. This arrow indicates that, or this blocking arrow shows that AMP stops PFK1, but then AMP stops ATP from stopping PFK1. Now, in this general area, and like I said, we're going to come back to citrate. In this general area, there's this rascal right here, F26BP. Now, you are absolutely right that it stands for fructose 2,6 bisphosphate. We haven't talked about that. Why haven't we talked about that? Well, because it's not an enzyme, or it's not a metabolite that is involved in glycolysis. It's involved in the regulation of glycolysis. So by proxy, yeah, it is involved in glycolysis, but we haven't talked about it because it's not like we pick up F26BP and immediately make pyruvate or something like that. I'm going to erase this so nobody gets confused about that and thinks that, yeah, that's what it does. So fructose 2,6 bisphosphate. Does anyone want to take a guess? Some of you may or may not be gambling people, but um, what do you think is the enzyme? And you can go with the acronym. What enzyme do you think makes fructose 2,6 bisphosphate? And as a little bit of a suggestion, PFK1 makes fructose 1,6 bisphosphate. What do you think makes F26 BP? I'll drink some of this sugar-free Barks root beer. Mackenzie, you're absolutely right. Kristen, Orion, it seems like I missed a bunch of people. You're absolutely right. PFK2. Okay. So PFK2 is an enzyme that is, I always like to think about it as kind of a release valve. Okay. So let me erase this real quick. Let me make sure that that's what I want to do. Okay. So the enzyme right here, PFK2, fructose or phosphofructokinase 2 makes fructose 6 phosphate or converts fructose 6 phosphate into fructose 2,6 bisphosphate. Now, a fair question is basically why? Well, one thing that's unique about this is that PFK2 is an enzyme. Yeah. Um, is an enzyme that is, sorry. It has two domains. It is reversible. So this is, Joel. It's the sequel. It's a reversible enzyme. It makes fructose 2,6 bisphosphate, and it also converts fructose 2,6 bisphosphate to make fructose 6 phosphate. So the way that I've always kind of thought about this and kind of personified it is imagine that you have a high glucose concentration. And let's imagine that the ATP concentration is a little bit low. Um, so we're not venturing into a place where we're inhibiting any of these enzymes. But I always like to think about it as let's say that we've got 1,000 copies of F6P. And let's say that you got 10 PFK1s. And if this is something that you think, well, I don't need that. That's trivializing this. I don't mean any disrespect. This is just what helps me understand this. I do tend to simplify things just for my own mind to wrap around it. So I have 1,000 copies of F6P, and I've got 10 PFK1 enzymes. Each one of those enzymes is going to be able to take one F6P at a time and make one F6 or 1,6-BP. Okay. So when 10 of those molecules are picked up, it's going to be able to go ahead and process that. And then it's just going to kind of turn over and over and over and over and over again. Now, this is going to kind of produce a little bit of a backlog. Let's say that this is taking place in the liver. What's going to happen? Well, all of this F6P that has accumulated is going to kind of, well, it's got a high concentration and it's going to inhibit which enzyme in the liver? Add it to the chat. You can go to acronym here. All of this F6P, these 990 molecules of F6P are going to block the enzyme. I see, yep, I see what you're saying there, Kristen. GK. You're absolutely right. It's going to block glucokinase. Now, whenever that happens, well, that's going to kind of slow down the flow or the flux of these metabolites through this entire pathway. Now, what we also have at play to kind of have another regulatory body there is we have PFK2. What PFK2 can do is it can take off, and let's say that we've got 20 PFK2s. Let's say we've got 20 copies of PFK2. In the first go round of these 1,000 copies of F6P, 10 are going to be picked up by PFK1, 20 are going to be picked up by PFK2, and that's going to kind of siphon off and make 20 F26 BPs. Okay. Now, does everyone follow that so far? Add to the chat a Y if you're good, or you can send me a private message of N or no if that doesn't make sense. Okay. Now, the significance of this is what are the implications of that? The implications are that, well, we've got 970 molecules of F6P as opposed to 990. These numbers are kind of arbitrary, but my point is our concentration of F6P that's going to be regulating and negatively inhibiting glucokinase is going to be reduced. What that's going to mean is we're going to be able to process this super high concentration of glucose because this PFK2 basically serves as a release valve. It's able to kind of, hey, I'm going to funnel some of these F6Ps over here. Just kind of, it's like, what are they? Squirrels, where they hide all their acorns and their cheeks and everything. I'm just going to stow this here temporarily. PFK1, when you're ready, what I'm going to do is I'm going to take that F26BP, and what am I going to do? I'm going to convert that back to F6P. And whenever I do that, then you'll be ready to use it. So we're funneling off this F26BP just as like a kind of simple storage stowaway. It's just going to hang out over here until we're ready to use it. Now, the significance of this is this item at the bottom. PFK1 is activated by F26BP. So if we were to jump back for a second and say, all right, well, we've got like one level, I'm going to label it level 1 of good is that, well, F26BP is a good F6P storage molecule. Does everyone follow what I mean by storage molecule? I'm just kind of setting it aside. It's not F6P, but it can be whenever I need it to be. Okay, great. Thank you very much, Trinity. So we're setting this F6P aside as fructose 2,6 bisphosphate. So that's the first level. Now, the second level of good that F26BP is F26BP. I always kind of think about it as like a activator of PFK1. So I just when I was a kid, I watched the Rocky boxing movies. I just imagine that PFK1 is the enzyme that goes back to its corner at the middle of each round. And it's like, can't go on, I can't go on. And then F26BP is there. He's like, no, you got it. And giving him shoulder rubs. And he's like wiping his face off and cut me, Mick. That was Rocky's trainer. So essentially, fructose 2,6 bisphosphate serves two different roles. One, it funnels off this metabolite that could be an inhibitor. The other role is that it activates PFK1. So it's almost like it's got a twofold positive effect on the activity of PFK1. So a fair question for that is, well, how? Why? I don't understand. Okay. So here's our compound, fructose 2,6 bisphosphate. It's a regulatory compound. It stimulates PFK1. Our enzyme, PFK2, makes it. Then this other enzyme, fructose 2,6 bisphosphatase, unmakes it. Unmakes it, I guess. I'll just go with unmakes it. Or deconstructs it. The significant point about this is that this is an enzyme that, get this, everyone, the same polypeptide chain. That is bonkers. PFK1, or sorry, PFK2, the kinase, I'm going to say kinase adds phosphate. And fructose 2,6 bisphosphatase removes phosphate. Those two functions, those two enzymes, are a part of one molecule, a part of one singular polypeptide chain. That's kind of crazy. Now, where or how did that happen? Chances are, if you've taken an evolution class, maybe you learned about um, genome duplications or chromatid fusions. Um, I mean, that's the kind of thing that I think about as to how this possibly happened. But that means that this enzyme that it's almost like my right hand my right hand uses a pencil and writes my name. My left hand uses an eraser and erases my name. So this is like constantly in flux, the amount of that's there. So this is a release valve that makes that fructose 2,6 bisphosphate, which activates and stimulates PFK1, but it also refuels and makes that fructose 6 phosphate. Now, this is a series of enzymes, this PFK2 and fructose 2,6 bisphosphatase. This is an enzyme that is going to be regulated, and it's going to be regulated by hormones like insulin and glucagon. Those are two hormones that are involved in, well, do we have too much sugar or do we not have enough sugar? Now, that's something that the depth of that you're going to go into in your metabolism class, should you elect to take that, which I strongly encourage you to. But that's kind of the function that this is taking. Now, can I get a response in the chat of, yeah, that sounds good, I got it, of just a Y or an N or something like that if you'd like me to kind of revisit this and go back. Okay, so I'm going to zoom out of this PowerPoint because what I want to do is share with you guys kind of what we've talked about so far. We've talked about two enzymes effectively. Our first or two steps. Our first step, the phosphorylation of glucose, and the phosphorylation of fructose 6 phosphate. So we've talked about G6P and F6P regulating um, hexokinase and glucokinase, respectively. F1P regulating the regulation by F6P. Um, and just to make sure, you guys see all of my slides right now, correct? Or all my screen with like 13, 15 slides? Okay, good. So that's where we first jumped into it. We were talking about the regulation of that first step. And then we went on to look at the regulation of our next step, our next major step, our um the the regulation of PFK1. So if you're thinking what's the takeaway from today, it's going to be these three enzymes, starting with those two. What are the regulators of these two steps, of these two processes? Um, in terms of specific hormones, I don't want you to stress about that for the activity of PFK2. Um, but I'd like to give you this as a kind of a good poll question regarding PFK2. Can everyone see that? Okay. Okay, so fructose 2,6 bisphosphate is blank of PFK1, an inhibitor, an activator, or unrelated to the function. So if you look at this, this shows that, well, where is PFK1? PFK1 is right here. And fructose 2,6 bisphosphate is an activator of this. That blue indicates that it's activating that. So if you're looking at that, it is an activator of PFK1. Okay, so now where we're going to go from here is we're going to move on to our next enzyme, our last irreversible step. And the majority of the class selected that it is an activator. I'm not going to share that poll. Well, I will. Okay, so pyruvate kinase. This is our last step in glycolysis. This is where we take phosphoenol pyruvate and we make pyruvate and ATP. So this is our last step in the whole deal. And this is kind of where we get to a stopping point on glycolysis with glycolysis. Now, this is an enzyme which is going to be activated by AMP and fructose 1,6 bisphosphate. Okay, so think about this fructose 1,6 bisphosphate is way upstream. That's almost like playing the role that F26 BP plays for PFK1. So we've got those two that are activators. Then we've got ATP as an inhibitor, acetyl-CoA, what? And alanine. Okay. Now we talked about alanine as being a metabolite that was a part of the Cori cycle. Lo and behold, if we've got alanine, we already talked about alanine being used to make glucose. So I'm going to go ahead and highlight that as part of the Cori cycle. We use this to make glucose. Can anyone add to the chat? And this might be a little bit longer of a response, longer than one letter. But if we use alanine to make glucose, then why would we want alanine to block pyruvate kinase or inhibit pyruvate kinase? think about our two big pathways, like those being glycolysis and gluconeogenesis. Negative feedback. Okay. What I'm thinking about here, and I think that you're on the same page as me, Orion, is that alanine, if we're using that to produce glucose, a gluconeo, or if we're using alanine for gluconeogenic purposes, then we want to kind of direct energy towards making glucose. Well, pyruvate kinase is the death nail in a glucose molecule. So it is a glycolytic enzyme. It's contributing to breaking down glucose. So alanine, we want to stop any enzymes that are involved in breaking down glucose. Because think if you were to do something where you convert alanine all the way into glucose, you wouldn't want pyruvate kinase and other glycolytic enzymes to be active to go ahead and through that process. Now, acetyl CoA, that's not something that we've talked about, but that's going to become very important in our post glycolysis world. Now, sorry, can I get a response as to if that was followed, a Y or an N? My explanation and commentary on alanine. Okay, okay, great. So since it's a precursor to gluconeogenesis, Trinity, yes, I couldn't have said it better myself. That I hate to say that because that sounds so pompous. But yeah, Trinity, great job. I really like that summary. That's absolutely right. Okay, so now we're going to go back to look at this big picture again. Alanine, we can use that to make pyruvate. We want to stop anything that is going to be involved in a glycolytic pathway. So that's one of the reasons that alanine is going to inhibit pyruvate kinase. Now, acetyl CoA. Okay, I haven't brought this up, but I want to now. This is our mitochondria. And in the event that you ever have the chance to look at any sort of cryo-EM images or something like that, you will be surprised to learn that a mitochondria is not just a green box with four pointed edges and the word mitochondria in it. So sorry to, let you down there. But here's our mitochondria, our artist rendering of mitochondria. This TCA cycle, also known as the Krebs cycle, also known as the tricarboxylic acid cycle, the first big metabolite in that is a molecule known as acetyl CoA. Acetyl CoA is a molecule that we're going to throw into the TCA cycle, and we're going to generate a bunch of NADH. We're going to further oxidize pyruvate down. And when we have a lot of acetyl CoA, well, that's effectively saying we don't need to be making any more pyruvate. We don't need to be going through producing anything more. So acetyl CoA is kind of a negative feedback or a negative regulator of pyruvate kinase. Now, ATP, again, if you're thinking about, well, why is ATP a regulator of any of our glycolytic enzymes? Well, then think about what's the point of glycolysis. Our big point of glycolysis, our purpose, yeah, there we go. Our purpose of glycolysis is to make ATP. ATP inhibits glycolytic enzymes and effectively says, you don't need any more. You got us. That's again my personification and anthropomorphizing. I don't know that word properly. Different enzymes. So ATP is going to inhibit those glycolytic enzymes because it's saying, hey, stop with this whole process because I'm here. I'm good. You don't need any more of me. Little does ATP know that it's a high energy bond that's going to be used. Okay, so those are our three big inhibitors of pyruvate kinase: alanine, acetyl-CoA, and ATP. Now, our activators of pyruvate kinase, I'm going to go back because one of them is AMP and another one of them is fructose 1,6 bisphosphate. Okay, if there's a lot of fructose 1,6 bisphosphate, then that metabolite basically says to pyruvate kinase, hey, let's get the wheels turning. Let's make more, let's expedite this process because there's a lot of me and my friends and we need to be metabolized. Now, the next item is, well, in addition to that, there are hormones that are going to regulate pyruvate kinase. Now, I'm giving you these as examples, but I do not need you to know about hormonal regulation of any of these enzymes. What I want you to focus on when it comes to regulation of these enzymes is I want you to focus on different metabolites. I want you to know that interchange there. So pyruvate kinase, though, just to kind of summarize this or not simplify this, but to share this additional detail, um, any enzymes that highlight kind of a preserve as much sugar as there is, like glucagon and epinephrine, those are going to be inhibitors of pyruvate kinase. Insulin, by contrast, which is the enzyme that your pancreas is going to make whenever there's a high blood sugar, that's going to activate pyruvate kinase. Okay, so there are levels of hormonal regulation. There are hormonal activators as well as inhibitors of pyruvate kinase. There are also hormonal activators and regulators of PFK2. Now, with that in mind, we've taken this is basically where we started, and we worked through it. What I think is the most important thing for you to do with this information is to remember those three big enzymes or those three big steps. I'll say steps as opposed to enzymes. I say enzymes because I think of glucokinase and hexokinase as being interchangeable, but those three big steps, those are the important ones. And as a result of those being the important ones, those are the ones that we're interested in understanding how they're regulated. Now, with that said, I've got a poll question for y'all. And this is our last poll question. We are most interested in the regulation of all of the enzymes below except, and I'll leave this one up here. And this is not so much a question of like, yeah, you'd find this in the textbook, or in a textbook, but this is more a question of like, what have we talked about and what have we like stressed and emphasized here? In addition to that, I think that these are also the important ones that you would see if you took any biochemistry or metabolism class. Um, I'm going to go ahead and end the poll right here. So share the results. 3/4 of the class selected selected aldolase. You're correct. Aldolase is a reversible step, though it doesn't really seem like it. And actually, I'll ask, could anyone tell me what aldolase does? You could say what it makes or what it breaks. Um, yeah, it makes glyceraldehyde 3 phosphate. It makes dihydroxyacetone phosphate and glyceraldehyde 3 phosphate. The way that I always think about aldolase, and why it confuses me that it's not a irreversible step is it takes a 6 carbon molecule and breaks it into two 3 carbon molecules, but breaks it into two uh, phosphorylated 3 carbon molecules. Okay, so I think that this was, I didn't, you know what? I included this slide, but I, it's not something I'm going to ask you any questions about. So this slide, it's number 9. Um, this is something that, I mean, we talked about it in the sense that lactate is used for making pyruvate and therefore can be used for gluconeogenesis, but I'm not going to ask any questions about this on an exam or a quiz or anything like that. So if you're thinking, what are the big things? Those 3 big steps. How are those steps regulated? How does, the questions that you should expect from me on your exam would be something like select all of the enzymes that are inhibited by ATP. In which case, if I have a list of enzymes, it might be select this, this, and this. Um, and then, another sort of question would be this enzyme is inhibited by ATP. However, that inhibition can be blocked by AMP, in which case the answer to that sort of question would be PFK1. Now, with that, that's kind of where I wanted to stop today. And I think that this is putting a bow on and kind of concluding our discussion of sugars. That's not to say I will not discuss sugars anymore. That's instead just to say, like, if you have any questions about sugars, I'd love to meet and talk to you about it. But that's kind of, I think that this gives you a really good working knowledge of sugar metabolism and the regulation of sugar metabolism. So I'm going to go ahead and stop my share right here. I've got a couple of minutes where I'll hang around, but if you don't have any questions, I hope you have a wonderful evening and I hope you have a great weekend. And reach out to me if you have any questions and I'll get back to you as soon as I can. Thank you very much for coming to class. You guys did a great job, great responses. I really, really appreciate it. Thank you very much. And